Right. Today we first come to the proofs we did in the last class geometrically. Thereafter, doing some questions, we can go to the next year part today. And those who were unable to watch the last Friday recording, I put that yesterday evening. If you are unable to watch it yet, people watch it and then complete the notes. This note should come after that. Okay. Right. So then today the very first part is write down the heading, not heading, as a question we'll write like this. Using geometric methods, prove that. Mod Z1 plus Z2 is then now equal to mod Z1 plus mod Z2. Number 2, mod Z1 minus Z2 greater than or equal to mod Z1 minus mod Z2. Third one, mod Z2 minus Z1 greater than or equal to mod Z2 minus mod Z1. Hence, deduce that modulus of Z1 minus Z2 greater than or equal to modulus of Z1 minus modulus of Z2. This one we proved in algebraically also. Right. And fourth one, mod Z1 plus Z2 greater than or equal to mod Z1 minus mod Z2. Hence, prove that mod Z1 minus mod Z2.
අනේ ඕක තියන්න නියොම්ම ඌල අවසන් එපා.
Right.
අනේ හොදන්න ඕ මේ ටික.
Right. This. Right.
ඕකද? ඕ
In the past paper, I can remember a small part involved in this inequality was to prove by using this geometric method. Using this geometric method, explain geometrically the reason why this happens. Okay, this one I can remember. This was to prove. Explain geometrically, given this becomes true. That was the question in that past paper question. But I, of course, included all possible proof. Then, of course, one out of this maybe, if it comes to the paper to prove all the things available here, then that also we can complete. Right. Here, to prove this, people, this is what we take. I take the Argand plane like this, right? In the Argand plane, This is the real axis. This is the imaginary axis. This is the origin O. I'll take this point P1, represent the complex number Z1, right? Then this is the line segment. We said what that complex numbers has the vector properties, right? And the other one, this is Z2. Suppose the point is P2, complex number is Z2. Then we can put this arrow like this. That gives the OP2 line segment represents the complex number Z2. Then I can construct the parallelogram with this OP1 and OP2 as the adjacent sides, right? Like this. Right. You see, right? No? This way we can take the parallelogram, right? This is parallelogram. Let this point be P. Then the point P will give the sum of the complex numbers Z1 and Z2. Then that is the line segment OP. This proof we did, people. Then this OP gives the sum of Z1 and Z2 by the line segment this. And then I join this P1, P2 line. This is the required diagram we should use to get these answers. Right. Then you can very clearly see, people, this OP line segment represents the complex number Z1 plus Z2. Okay. Then OP length is equal to modulus of Z1 plus Z2. Therefore, OP length is modulus of Z1 plus Z2. Right. OP1 line segment gives us, people, complex number Z1. Then OP1 length is equal to mod Z1, right? OP2 line segment gives us complex number Z2. Then OP2 length is equal to mod Z2. Mod Z2. This I think you can very easily understand. Okay. Right. Now, people, another thing is this you should know under this, improving this all. When we consider a triangle, for the convenience of our consideration, I am going to take a right angle triangle. A right angle triangle. Now, suppose we consider a right angle triangle like this. Consider this right angle triangle. A, B, C. I can take this as 3, then this is 4, then this is 5. When we consider people any triangle, any triangle, huh? When you consider any triangle, yeah, when you consider any triangle, people like this, 3, 4, 5, in any triangle, sum of any two sides, sum of any two sides, let's see here, AB plus BC, sum of any two sides, greater than or equal to the third side. See here, AB is 3, BC is 4, AC is 5. 3 plus 4, 7, right hand side 5 greater. Okay, equal sign, I will explain the situation. Now, next thing is, suppose I'll take this way, AC plus CB and consider AB. Sum of any two sides, AC is 5, CB is 4, AB is 3, when you consider here, greater, like this. So therefore, the first result here we have used is, when we consider in triangle, sum of any two sides of the triangle is greater than or equal to third side. This equal sign become valid, people. Now consider this triangle. Okay, consider this situation. I take this way a circle, right? Now I draw a triangle like this. So right angle triangle. Right. This is O, this is A, this is B. About now this is 3, 4, 5, right? Now people, without changing the points O and A, points O and A are fixed. Now suppose this point B, we bring along the circle this way. Then points O and A are fixed. They are not changed. Point B only we take along the circle. Now suppose the resulting triangles. This way we get another triangle. Still that greater than sign is valid. That means sum of any two sides greater than to the third one. When the point B is here, the triangle is this. When the point B is here, triangle is this, right? Still, sum of any two sides of the triangle greater than the third side. This greater than sign is valid. Like that, people, one occasion, the area, you can see once this point B coming this way, the area of the triangle is decreasing, reducing. One occasion, this area becomes 0, people. That occurs when the point B comes here. Then the triangle is a straight line, say, straight line. Then OA plus AB, OA plus AB greater than OB. This greater than sign become valid, people. Greater than sign become valid until the point B comes up to this, just before B, not at B. At B, you can see this side. That means this AB side is equal to this. OA side is this, AB side is this. And this OB side is, when the B comes here, equal to this. Then the equal sign become valid. Then this equal sign become valid when the triangle has a 0 area. That is the case, the equal sign valid. Okay, right. So that is the first thing you should understand here. And people, the next one is difference of any two sides. In the same way, we can say when you consider difference of any two sides, BC minus AB. Difference of any two sides of a triangle is smaller than or equal to the other side. See here, BC is 4, AB is 3, AC is 5. Then here we get 1, here 5. Greater than sign become valid. Okay. That is the second one we have to use. What is that? Difference of any two sides of a triangle is smaller than or equal to the third side. Again, this equal sign, people, become valid when the triangle is a straight line, when its area becomes 0. Okay. This is how we get the results. Okay, so then from there we start. And here you can very clearly understand this OP1, P1P, this is a people parallelogram. Then this OP2 and P1P are equal. OP2 is equal to OP2 is equal to P1P. P1P, right? Okay. Then first a draw diagram, and then we'll write one sentence. We'll write one sentence. Write down like this. Let the complex numbers Z1 and Z2 are represented by the points P1 and P2 respectively on the Argon diagram. The Argon diagram. Right now construct the parallelogram OP1PP2. OP1PP2. Right. Then you can write this data. Right, people. Another one data you can write here. P1, P2. Use the complex number P1, P2. Z2 minus Z1. Then P1, P2 length equals modulus of Z2 minus Z1, no? P1, P2 length. And also P2, P1 length. P2, P1 length. P2, P1 line segment gives us the complete sum Z1 minus Z2, P2, P1. Then P2, P1 length going to be the modulus of this. Right. Now you can write, put a star mark, and then you can write first one like this. Write in the first one. Write down the sum of SVM sum. The sum of any two sides of a triangle is greater than or equal to its third side. Second point, write down, people. Number 2. The difference of any two sides. The difference of any two sides of a triangle is smaller than or equal to its third side. Right. Then we can prove one by one here. First one. By the diagram, you can now write, people, this way. OP1 length plus P1P length greater than or equal to OP length. OP1 mean modulus Z1 and P1P, P1P equals OP2 equals modulus Z2. OP is Z1 plus Z2 mod. So in modulus Z1 plus modulus Z2 greater than or equal to modulus Z1 plus Z2. First one is coming. Right. Now, people, I am going to consider next one like this. Here, I take OP2 P1 triangle. This is by, I write here, by OP1 P triangle. Second one, by OP2 P1 triangle. You can again write, people, OP2 plus P2 P1, sum of two sides of the triangle. greater than or equal to people, what? OP1. Correct, no? Sum of any two sides of a triangle greater than or equal to its third side. OP2 mean people mod Z2. P2 P1 mod Z1 minus Z2. OP1 is mod Z1. Then bring this right hand side. This one coming. The second one is okay, no? Third one. Again, we take this OP1 P2 triangle by OP1 P2 triangle. Again, you can write OP1 plus P1 P2 greater than or equal to OP2. OP1 is mod Z1, P1 P2, you know people, P1 P2 is Z2 minus Z1 mod. Greater than or equal to OP2 mod Z2. Right. Then you can subject this. Mod Z2 minus mod Z1. That way we get the third answer. Now people asking next one, hence reduce this answer. Yeah. Now suppose we have x greater than or equal to a minus b. Second statement we have x greater than or equal to b minus c. Now when we have these two statements together like this says x greater than or equal to a minus b. This says x greater than or equal to b minus c. When we consider people this a minus b and b minus c, one of these two is bigger. That can be a minus b or b minus c. That biggest value, people, without knowing exact values of a and b, we can't determine. But that biggest value can easily be found taking any of these two, and once you take modulus, that biggest value can easily be found. So therefore, this says x is greater than a minus b, x is greater than b minus c, mean either this a minus b or b minus a is greater. This statement says that x is greater than the biggest value or the bigger value of these two. To get the bigger value, people, very easily we can taking any of these two, take the modulus, then we get the bigger value. So therefore, here you have in number 2, this greater than or equal to this difference. This one says the same thing, right? Z2 minus Z1, right? Greater than or equal to this. Then what is asking to prove? Z1 minus Z2. People, you can very clearly see, this mod Z2 minus Z1. You can very clearly see here P to P1. Since P to P1. P to P1 is this, no? Is equal to P1 P2. Right? P1 P2. Same line, no? P to P1 length and P1 P2 length being equal. P to P1 is this. What is it? 1 minus Z2. P1, P2 mean people this. Right. Then here for this Z2 minus Z1, I can put what? This is Z1 minus Z2 because these two are equal. Therefore, we may write by 3 by above result. But people, this one I can write mod Z1 minus Z2 greater than or equal to mod Z2 minus mod Z1. Also, the same thing we have proved here. Mod Z1 minus Z2 greater than or equal to mod Z1 minus mod Z2, like this. See here, the same thing available in the left hand side. Right hand side we have different order. Therefore, people, I can write this one greater than or equal to modulus of one of these two. I will take modulus of this. Then we get the next answer. Write down the next one. Therefore, mod Z1 minus Z2 greater than or equal to modulus of mod Z1 minus mod Z2. Okay. The algebraic proof of this same thing, people, available in the previous recording, last Friday recording, I put to your group also. Please take that and complete that note. In the past papers, when you go through these past papers, those proofs available. If you are asked to prove this geometrically only, people, we go for this method. Otherwise, you have to use the geometric method. All the geometrical proof available in that recording. Right? Some of you have obtained that recording, and the others, please take and complete the notes. Right? Okay. Now, that thing we did. Okay, the fourth proof is people. Right. Fourth proof is this. Right. We can consider to get the fourth proof like this by OPP1 triangle. By OPP1 triangle, I can write, people, OP1 length minus, right, P1 P length. OPP1 triangle means this triangle. In the triangle, OP1 and P1P are two sides. I take the difference of these two sides. That difference, people, less than or equal to third side. There we use the result that difference of any two sides of a triangle is smaller than or equal to its third side. Then you can very clearly see here OP1 is mod Z1, P1P, people we know, P1P is mod Z2. OP length means mod Z1 plus Z2. Right? Difference of any two sides of a triangle is smaller than or equal to third side. So then this gives us the required answer. And number 5. Fifth one can easily be obtained, people. Very first proof, by the proof of 1, we proved what? Z1 plus Z2 mod smaller than or equal to mod Z1 plus mod Z2. These two we can combine now. Therefore, we can write therefore mod Z1 plus Z2. This one smaller than this. By number 1 we proved that smaller than or equal to. And by number 4 people we proved that is greater than or equal to this. This is how we do this proof. Right. I will come to some questions under this inequality part, people. Write down this question. Part A, if Z is any complex number such that mod Z4 less than or equal to 3. Find the greatest value of mod Z plus 1. Part B, if Z is a complex number such that mod Z minus 2i less than or equal to 4, find the greatest value of iz plus z naught mod. modulus of iz plus z naught, where z naught is equal to 6 plus 3i. Even now, these answers we can obtain by using these theories we proved. First one is Z is any complex number such that Z plus 4 modulus is less than or equal to 3. Find the greatest value of Z plus 1. Right. Now, answers I can write. We need Z plus 1 modulus greatest value. This mod Z plus 1 we can write mod Z plus 4 minus 3. Okay, no? This one you can write Z plus 4 is one complex number plus this one I write as minus 3, another complex number. This is Z plus 1. Okay. Now you can use that to solve what? But since Z1 plus Z2 mod is then or equal to mod Z1 plus mod Z2. This one you can now consider as this one Z plus 4 plus minus 3. Yes, people here. This is your Z1 complex number. This is your Z2 complex number. People, any real number you know a complex number? No? Then we can apply this. Z1 plus Z2 smaller than or equal to mod Z1 plus mod Z2. Then this is less than or equal to mod Z plus 4 plus mod minus 3. But people, you know, this whole thing is nothing but this one. No? There you have mod Z1, mod Z plus 1 is then or equal to mod Z plus 4 modulus of minus 3 is 3. Right. Okay, now people now here we need to find Z plus 1 greatest value. Z plus 1 modulus greatest value. Now we are having here mod of Z plus 4 less than or equal to 3. Less than or equal to 3. Then to find the maximum possible value this right hand side can take, to get the maximum possible value the right hand side can take, we have to put for this Z plus 4 modulus maximum value. Then you can write for the right hand side to be maximum. this right hand side to be maximum. We have to put for the Z plus 4 modulus maximum value. People, according to this Z plus 4 modulus, either less than 3 or equal to 3. Then what is the maximum value of this Z plus 4 modulus? 3. It is 3. Then Z plus 4 mod should be equal to 3. Okay. Then the maximum value on the right hand side, people, gets this when this takes 3. Therefore, mod Z plus 1 less than or equal to 3 plus 3. Then we get 6. Mod Z plus 1 less than or equal to 6. Then you can see what is the maximum value this Z plus 1 mod can take. It is 6 now. Therefore, mod Z plus 1 max equals 6. Right now, yeah. Count second part. Right, second part is this. Z is a complex number such that Z minus 2i mod less than or equal to 4. Find the greatest value of IZ plus Z naught modulus. Right. I can first write modulus of IZ plus Z naught. This one I can write like this, people. Since we need to use this, we have to form this one where on the right hand side of this. Then I can form it like this. I times Z minus Z naught. Wait. I write it like this, modulus of I Z minus 2i plus 2i squared plus Z naught. All right. See here what happens. Here we have 2i, right? We have 2i. Then what we get there? We get I Z and Z naught. Here minus 2i squared and plus 2i squared cancel off. Then on the right hand side, we have IZ plus Z naught only. Right. Now I can write this way. I times z minus 2i. These people, 2i squared is, I squared is -1, no, -2. And this z naught given 6 plus 3i. This is then iz plus z naught, I can write modulus of I z minus 2i. Here 6 minus 2 is 4 plus 3i. Right. Now I can consider this whole thing z1, this as z2. Okay. You can now write, since what people? z1 plus z2 modulus less than or equal to mod z1 plus mod z2. We can apply this portion. I am going to write via here modulus I times z minus 2i plus 4 plus 3i. This is your whole thing is z1, z2. This is less than or equal to people. Mod z1, mod of this I times z minus 2i mod plus mod of this 4 plus 3i. People, but what is this? This is this, no, it is this. Therefore, I can write for this. This is modulus of iz plus z naught less than or equal to. Here, I is a complex number. Z minus 2i is another complex number. Then here we have a product of two complex numbers and its modulus. Product of two complex numbers and its modulus, like this. People, we have proved this one as z1 mod into z2 mod. We proved this. So therefore, I can apply that modulus for this I separately and modulus of this z minus 2i separately. And you know what is the modulus of this 4 plus 3i? Modulus of a complex number is what? Real part perfect squared plus imaginary part perfect squared root. 4 squared plus 3 squared root is 5. Right. Now, you know here, people, modulus of I is 1. That we know. One times this. Now, as before, people, z minus 2i, we are given z minus 2i less than or equal to 4. You can now write, since z minus 2i mod less than or equal to 4, for the RHS to be maximum, for the RHS to be maximum, this z minus 2i modulus should be, people, equal to 4, no? Z minus 2i modulus less than or equal to 4. Then maximum value of z minus 2i modulus is 4, people, right? Z minus 2i mod should be equal to 4. Therefore, now you can write this result. Modulus of Iz plus Z naught less than or equal to, this is 4 plus 5. This is 9. Okay. Then you can write Iz plus Z naught modulus less than or equal to 9 mean people maximum value. Therefore, Iz plus Z naught max is 9. Max is 9. Right now, that's how we take that answer. Involved in this inequalities get of course solved in this way. Question available people in past papers, you can now work out them. Right now we people come to the next theory part. This is the last theory part, except that De Moivre's theorem, and then we can come to De Moivre's theorem. That will be the end of the all theories in the lesson. Right. I will come to that now. Write the heading as cube root of 1. Cube root of 1. Right, people, now when I consider x squared equals 4, then how to write this x plus or minus square root of 4? The square root mean what, people? X is equal to 4 to the power half. Right? Then you can very clearly see here this x squared equals 4. The solutions of x, the solutions of x give us square root of 4. That is meaning, because here x is equal to 4 to the power half. Now another one we may consider x cube is 27. Then can somebody tell me, by solving this equation, for what? For x, what we get? For x we get, when you submit x, we have to take 1/3 power on both sides, no? 27 to the power 1/3. When you solve this equation for x, we get some answers for x. The answer of x gives us cube root. 1/3 power means, people, cube root, right, of 27. So this one again we write this way: 3 here, 27 here, cube root. So therefore, understand here, x power 3 equals 27. This equation we solve for x. We will get 3 answers for x. We will get 3 answers for x. That each answer of x gives us cube root of 27. Then, can you tell me, if I need to find cube root of 1 means 1 to the power 1/3. Cube root of 1 means 1 to the power 1/3. To get the answer of 1 to the power 1/3, can you tell me what kind of equation we have to solve for x to get this answer? We have to solve, people, x to the power 3 equals 1. Why? Then only when we subject x, you write this as 1 to the power 1/3. You might say, people, x cube equals 1 mean x equals 1. Then why do you worry about this equation more? People, that x cube equals 1 gives us x equals 1. True. People, this x equals 1 is only one solution for x. When we solve this equation, we get. That is the real solution for x. But when you solve this x cube equals 1 equation for 3 answers of x, you will see another 2 answers we have for x. Those 2 also give us cube root of 1. Those 2 answers, people, imaginary answers, complex numbers. That is why we straight away say x cube equals 1 implies x equals 1, because here, so far, when we solve some equations, this x we considered as real number. Then the answer of x should be real. That is why straight away we took this x equals 1 as our answer, neglecting the other 2 complex answers. But this time this x is a complex number. Then there are 2 complex answers, people, this time we can't neglect. Understand? So then there are 2 answers when we consider, there are basically 3 answers for cube root of 1. Of them, 1 is a real number, that is 1. The other 2 are, people, complex numbers. Now we are going to find out them. Understand? Okay, right. So now you know really what is meant by here. Okay. Now we'll write like this. Write down cube root of 1 means, people, this, within bracket you can write 1 to the power 1/3. One to the power 1/3. Right. All right, on like this one sentence. Consider the equation x cube equals 1. X cube equals 1. Then x is equal to 1 to the power 1/3. X is equal to 1 to the power 1/3. Right, and therefore, the solutions for x, the solutions for simple x in the equation x cube equals 1 give the values of cube root of 1. Cube root of 1. Okay. Now, people, I am going to solve this equation x cube equals 1. X cube equals 1 equation I am going to solve. Now I take this 1 to this left hand side, and this 1 we can write as 1 cube, 1 to the power 3, any power of 1 is 1, no? Right? Now here I factorize this using difference of 2 cubes. X minus 1, x squared, plus this product 1 squared is 0. This is x minus 1, 0. And people, in a usual question, we ignore this part, saying this doesn't give us real solutions for x. Whenever in the considered question x is real number, this doesn't give real solutions, then we ignore this. When you consider the discriminant of this, delta b squared minus 4 times 1 into 1, you can see this is minus 3. That is why we say this quadratic expression doesn't give real solution. Then in a usual question, when x is real, we ignore that. But this time we can't ignore. We expect the solutions of x which are imaginary also. And then this one you can write x squared plus x plus 1 equals 0. Then here you get 2 imaginary answers for x. But that x answers are cube root of 1. Then 2 answers coming from here for cube root of 1. Another answer coming from here, x equals 1. Then finally, since there are 3 answers for x, there are 3 answers for cube root of 1. Understand? Right. Then we take that. First one is this. X equals 1. Let's see to find the solution of this. Then here we get x squared plus x plus 1 equals 0. X equals minus b is 1 plus or minus square root of b squared 1 squared minus 4 times 1 c divided by 2 into 1. Here we can write 1 minus 4 divided by 2. X equals minus 1 plus, so minus here minus 3 root. Right now. Now I can write this like this. 3 times I squared divided by 2. Then you get x equals minus 1 plus, so minus root 3. I take root of this and root of I squared. This side divided by 2. Then we get one answer for x. Take this plus sign, minus 1 plus root 3i by 2. Another one, x equals minus 1 minus root 3i by 2. This way, two answers we get. Then altogether, there are three answers for cube root of 1. One is this value 1. Other two are this and this. Okay. Then write down one sentence. Write down like this. Therefore, there are three solutions for cube root of 1 of cube root of 1. There are three solutions for cube root of 1, and of them, one solution is real and the other two are imaginary. Within bracket, write down complex numbers. Within bracket, write down complex numbers. Right. Okay, now x equals 1. X equals -1 plus root 3i by 2. The other one is, people, x equals -1 minus root 3i by 2. Right. The other solutions. Now, I'm going to consider, people, this complex root dividing by 2 separate these. The other one like this. Okay. Now you can see, when you consider this two complex roots, complex answers, when you consider this is a complex number, it takes form x plus yi. Then taking this sign to opposite available here. Then we can see, first thing here, people, this complex answers, the imaginary answers of cube root of 1, they are mutually conjugate. Mutually conjugate means of this one, conjugate is here. This one conjugate is this. So therefore, people, this is not the important one. What is the property? When some equations, we can't say, people, always the equations should give real solutions for x. There are some equations which give, as here, real solutions and imaginary solutions both. Some equations there are all solutions are imaginary solutions. Some equations there are all solutions are real solutions. Some equations are there, people, some of them are real, some of them are imaginary. In this way, people, when an equation gives imaginary solutions, remember, those equations always give imaginary solutions as conjugate pairs. Conjugate pairs. What is meant by conjugate pairs? Conjugate pairs means, people, like this. If one solution is imaginary, definitely in the same equation, another solution come in as the conjugate of this. That is why this is known as conjugate pairs. So therefore, remember this one. When equations give imaginary solutions, those equations always give imaginary solutions as conjugate pairs. Therefore, any equation, if it gives imaginary solutions, always the number of imaginary solutions should be even numbers. Even number of imaginary solutions should give. Why? Any equation, if it gives imaginary solution, it gives the imaginary solutions as how people conjugate pairs. Complex number and its conjugate. Then two imaginary solutions available there. There cannot be three imaginary solutions. Why? Third one occurs, meantime, its conjugate also coming. Okay, that is the next thing you have to understand by this. Okay, now I am going to take out of these two any imaginary solution as omega. That is the standard notation to denote the imaginary solution of cube root of 1. Or write down, let omega be any imaginary solution of cube root of 1. Of cube root of 1. Now I take let. I take this one as our omega. Minus 1 plus root 3 by 2 I. Then people, the other one is well obvious, omega bar. Write down then the other root is omega bar. Right, people, the other thing is, though you take this as your omega, then still this statement become true. If this one is your omega, its conjugate is people this. Right. So then that is first property you have to understand. If omega is any complex solution for the cube root of 1, then the other one is omega bar. Right. Then people, the other thing is this. See here. I took this as our omega. I am going to take omega squared. Omega squared means 1 minus half plus root 3 by 2i square this. And simplify this. What do you get? Omega squared 1 by 4 minus, what do you get here? This into 2, no? We get root 3 by 2 I. This into 2 plus 3 by 4 I squared minus 1. You simplify this, what do you get? Here 1 minus 3 minus 2 by 4 minus half minus root 3 by 2 times I. Like this we get. Well, what is that? It is the other root, no? When you take one complex answer of cube root as omega, after squaring that, we get omega squared, no? That omega squared is this. So therefore, another relation we have, people. What is that? If one solution, imaginary solution of complex solution of cube root of 1 is omega, the other one is omega squared. Then if you take this as omega and square in this, you can see you get this. They will write that statement also. Write down like this. Therefore, if omega is one complex, omega is one complex solution of cube root of 1. Then its other complex solution is omega squared. Omega squared. Omega squared. Right. Another relation here we have, people. What is that? Omega, I am going to take like this. Minus half root 3 by 2. I know. People, I am going to take the reciprocal of this omega. 1 upon omega. One upon omega, when I take, people, I have to take reciprocal of this, no? 2 upon minus 1 plus root 3i. Now, I multiply on the right hand side by the conjugate of this. Conjugate. See. Right. Now simplify this and see what we get there. Simplify this. One upon omega. Here you can write this one as a squared minus b squared, no? When you take this minus sign out, that one you can write 1 plus root 3i. The other one you can write as root 3i minus 1. A plus b into a minus b. This minus sign and this minus sign, so you can simplify. You get 2 times 1 plus root 3i divided by here a squared minus b squared root 3i perfect squared minus 1 squared. Simplify this. Root 3 squared is 3, I squared is minus 1. Minus 3 minus 1. What is this, people? Minus 4 cancel down. Minus 1 minus root 3 by 2. I. What is that, people? Again this, no? If you take this as our omega, its reciprocal 1 upon omega is this. Then, people, another relation we have. If complex arms of cube root of 1 is omega, the other one is 1 upon omega. 1 upon omega. So therefore, there are three properties. If omega is one complex root of cube root of 1, the other one is omega bar. The other one is omega squared. The other one is, people, 1 upon omega. Understand? Right. Then you can write that also in a sentence. Add on, if omega is one complex solution of cube root of 1 the other complex root of cube root of 1 is 1 over omega. Right. Okay, next one, people. Now this is our omega squared, no? Right, no? We said no. We said this as our omega squared, right? Now we can write. Now omega is this. Omega squared is this. Right. Now you can write omega plus omega squared. Add this omega and omega squared. Then what can say? Root 3 by 2 I here will cancel with this minus half, it's minus 1. Take this minus 1 this side. Then what do you get? 1 plus omega squared equals 0. Right? Right, people. The next one is this. People, we said when this is omega, we said this can be obtained by taking 1 upon omega. But in previously we said what? This is omega squared. This is omega squared in one simplification. In the last simplification, we said, people, this is 1 upon omega. Right? So therefore, this is omega squared. Same thing is coming by 1 upon omega. The same thing, this is coming as 1 upon omega. Therefore, these two must be equal. Then using cross multiplication, we can say omega cube equals 1. Also, we can write this is your omega squared. And you said that can be obtained by 1 upon omega. Then that two must be equal. Therefore, omega cube equals 1. Right? Omega cube equals 1. Therefore, this relation and this relation, very useful relations, people, in solving questions, remember. Right. Next one, we can prove this omega cube as 1, people, directly multiplying this and this. That also another possibility, right? We'll show that also. Or I don't like this. I don't know. Omega cube equals omega into omega squared. Omega cube. Omega is this. We'll take this. Minus 1 plus root 3i by 2. Then omega squared is this, no? Take this 2 out. Then 4. Take this minus sign out. we get root 3i plus 1, root 3i minus 1. Then simplify this. We get 3i squared minus 1. I squared is minus 1, minus 3, minus 1 is minus 4. Here minus 4, this is omega cube is 1. Omega cube is 1. That way is another solution to show this omega cube equals 1. Right now? Right. Right. Now let's see, people, the modulus, the polar form especially of this omega and omega squared. Right. Okay. We'll come to that now. This is okay, no? Right. Now you can write polar form of omega and omega squared. Omega, people, this, no? Minus 1 upon 2 plus root 3 by 2i, and omega squared is this. Right, people, now here, how to take the polar form? Yeah, this one I can consider. This, you know, real part is minus half. Imaginary part is root 3 by 2. Huh? Minus half root 3 by 2. Imaginary axis, real axis. This is a complex number. Line segment that represents the complex number. Okay. Then this angle I can write tan theta. Opposite side root 3 by 2 divided by adjacent side half. Opposite by adjacent, these two can cancel down. Tan theta root 3 means pi by 3. Okay. Right. So then this is the angle we need to take in writing the polar form, that is 120. Right. And suppose this point is P, then OP length. What is that? Square root of minus half squared plus root 3 by 2 perfect squared. What do you get there? Here 4, here 4. 3 plus 1, 4. 4 by 4, 1. OP 1. What is that, people? Arg of omega. Not pi by 3. 120, yeah? 2 pi by 3. Modulus of omega. OP length, no? 1. Similar, we can come to this omega square. Then omega you can write how, people? Omega you can write f omega. You can write 1 is the modulus cos 2 pi by 3 plus I sine 2 pi by 3 is omega in polar form. Now come to this omega squared. Come to this omega squared. Omega squared minus half minus root 3 by 2y. Minus half is here, minus root 3 by 2 here. Point suppose here. This is suppose Q. Then if I take this angle as alpha, tan alpha, you can write people. Tan alpha is opposite by adjacent. Then again alpha. Pi by 3. And this OQ length. Minus half perfect squared minus root 3 by 2 perfect squared. This is 1. Then you can write polar form. What is the polar form, people? Is 60 no? Then we can take the positive sense. Though the principal part exceeded, never mind. Then what is the polar form? Omega squared. Modulus is 1. Arg omega squared is pi plus pi by 3. 4 pi by 3. And the modulus of omega squared 1. Okay, now polar form you can write omega squared 1 cos 4 pi by 3 plus I sine 4 pi by 3 is the polar form. Okay, omega and omega square, the module values, people, each one module value is 1, right? Okay, now I can represent, people, there are 3 answers for cube root of 1. One is 1, other one is omega, the other one is omega square. Now I am going to represent them all on the Argand diagram. Okay, now write down values. Right. Write down the 3 solutions. Write down that. Let represent the 3 solutions of 1 to the power 1/3 on the Argand plane. On the Argand plane. People, what do you get? Yeah. I'll take here. This is omega squared. This is 1 omega squared. This angle is 60. The other one is omega here. P. This is 60. This length is 1. The other one is real 1, no? Here. Suppose this is R. This length also 1 people. No? Omega here, omega squared here, 1 here, R. Even now you can see, when we draw a circle, taking the origin as the center and radius as 1. Taking the center as this origin and radius as 1, that circle passes through these 3 points P, Q, and R. So therefore, by this we can say the answers of cube root of 1 lies on a circle on the argand plane with center at the origin and radius as 1. And also people, when I join this P, Q, and R, we get a triangle. We get a triangle. In that triangle, you can see PQR, when we join, this PQR triangle going to be equilateral triangle. See here. Right? So then here we have a point. This way we have no. Right. Then this length and this length being equal. This also the same. This is 120. Here, this is 120. Right? This is 120. Then people, you can see this triangle, this two congruent, this two congruent, this two congruent. Therefore, these 3 sides are equal. Therefore, this triangle is equilateral triangle. Then you can see the solutions of cube root of 1 lie at the vertices of an equilateral triangle on the argand plane. Understand? All right. First draw this one and we'll write those two. Yeah. You will of course find some questions. You come across some questions show that the solutions of cube root of 1 lie on a circle with radius 1 and center at origin. Also show that they lie at the vertices of an equilateral triangle on the argand plane. Then this way we have to prove that. Yeah, first draw and then write. Write down like this thing. The 3 solutions of 1 to the power 1/3 lie on a circle, lie on a circle, lie on a circle with radius 1 and center at the origin. And also they lie at the vertices of an equilateral triangle, on the Argand plane. On the Argand plane. Right. The next important one here we must write, people, when an equation gives as its solutions complex numbers, imaginary solutions, then that equation should give the solutions, complex solutions, we say usually. For the imaginary solutions, we say complex solutions. The complex solutions are always coming with conjugate pairs. If one complex solution is coming, meantime, by the same equation, its conjugate also given. Therefore, when we consider an equation which gives complex solutions, the number of complex solutions should always be an even number because they occur as conjugate pairs. Okay, so when particular equation gives 5 solutions having both real and complex solutions, right, people? When particular equation gives 5 solutions having both real and complex solutions, definitely that equation should have 2 complex solutions and 3 real solutions, or 4 complex solutions and 1 real solutions, because complex solutions never occur alone, they always occur as conjugate pairs. Understand? Okay, then we'll write that also. Put a star mark. Right, write down like this. When an equation gives complex solutions the complex solutions always occur as conjugate pairs. Conjugate pairs. That is, complex number and its conjugate. Complex number and its conjugate. Both occur as the solutions. Therefore, when an equation gives complex solutions, then the number of complex solution should always be an even number. An even number. An even number. Right. Okay, now people, taking your tutorial, the question number 25. Take question number 25. Take question number 25. Question number 25. Right. See, what is question number 25? Find the roots of the equation x cube minus 1 equals 0. That means the ones we have already proved. Okay. If one imaginary root of this equation be omega, then show that the other imaginary root is omega squared. Right? Hence show that 1 plus omega squared equals 0. That also we proved just now. Show also that the complex root is the reciprocal of the other complex root. That also we did. Now show that. Come to first one. 2 minus omega squared, 2 minus omega 7, 2 minus omega 8. We have to prove this is equal to 49. People just try to take this answer. It's very easy part. People, how take it? Yeah, I can do it like this. First, I write these two brackets, first two brackets together. 2 minus omega. 2 minus omega squared this way together. Two minus omega 7. This way together. People, without proof, you can directly use the results this. 1 plus omega squared equals 0. And omega cube equals 1. These things you can directly use without proof. Wherever you work out involving omega this way, this results without proof you can directly use. Then simplify this. 2, 2, 4 minus 2 omega squared minus 2 omega plus omega cube. Here 2 and 2 make 4 minus 2 omega 8 minus 2 omega 7 plus omega 15, no? This way. You take minus 2 out. Omega squared plus omega. Omega cube is 1. Here 4. Take people here. Minus 2 omega 6 out. Then here we get minus 2 we took out, omega 6 out me omega, here omega squared. And omega 15 we can write omega to the power 3 to the power 5. Like this, huh? 4 minus 2 omega plus omega squared. Here omega plus omega squared means take this one to right hand side, minus 1 plus 1. And this one, people, 4 minus 2 times omega 6 I can write omega to the power 3 to the power 2 like this. Omega plus omega squared. Take this one right hand side, minus 1. Omega cube is 1 to the power 5, like this. Here we get 4 plus 2 plus 1, it's 7. Here 1 squared, then 1 minus minus plus 4 plus 2 there, 1 7, then this is 49. That's how we take the answer 49. Right, people, take it second part. Take it second part. 25, question number 25, part 2. Given that a plus b omega plus c omega squared divided by c plus a omega plus b omega squared is equal to omega squared. Right, take this. Take this answer, people. People, to take this answer, we'll do this way. I am going to multiply this numerator and denominator by omega squared. Then it won't change because we multiply by omega squared both the numerator and denominator. And here. Now simplify this. Right, so then once you remove the bracket by multiplying this omega squared, the numerator a omega squared plus b omega cube plus c omega 4. No, we'll keep this numerator omega squared like that because the answer is to show as omega squared. No, we'll keep the numerator omega squared as the same. We'll multiply the denominator by this omega squared, c omega squared, a omega cube, b omega 4. This is a plus b omega plus c omega squared. Here, omega cube is 1 people. A into 1 is a. B omega cube I can write b omega 4. No, I can write that as omega cube into omega. Omega cube is 1. B omega. And c omega squared. like this. This you can cancel down, people. Then we get omega squared. That's how we show that. We will now take in the same page, page number 10, under question number 27, second part. Question number 27, part 2. Right. Right. 27 part 2 is the next. Question number 27 part 2. Yeah, there you are given let Z be a complex number and omega be the cube root of 1. That is given. If mod Z minus 1 less than 2n, omega Z minus 1 minus omega squared modulus equals, say, show that A less than or equal to 4 greater than or equal to 0. Yeah. You are given this, people. Z minus 1 modulus less than or equal to 2. The other one, modulus of omega Z minus 1 minus omega squared equals C. Right? Then asking to show this A, this less than or equal to 4, greater than or equal to 0. This one only we need to prove. Right, so then I'm going to write it like this. This one only A. So therefore, I'm going to take this one, modulus of omega Z minus 1 minus omega squared. This one I'm going to write like this. Omega Z minus omega plus omega minus 1 minus omega squared. Never mind, no, because minus omega plus omega we can cancel down. Then we have omega Z minus 1 minus omega squared, the same thing. Right. So then this is what I do next. Omega from this 2 we can take out, Z minus 1 plus here omega minus 1 minus omega squared. Well, you know, this 1 plus omega squared is 0. We proved that. Then I can take this 1 and this omega squared to right hand side. Then we get minus 1 minus omega squared. It is omega. That is this. Minus 1 minus omega squared. It is omega. Then we have modulus Z minus 1 omega time plus omega. This is really plus omega, no? This way you can take. Then here's nothing but 2 omega, and you can now take omega out. Z minus 1 take omega out. The bracket is Z minus 1 plus 2. We have like this. Right. People, now you can very clearly see here, when you consider this whole thing, it's a complex number, no? Z is a complex number. Z minus 1 is a complex number. Adding to that another real number, this is a complex number. Then here we have product of these two complex number, its modulus only available. That modulus of product of two complex numbers we can write this way as a product. Like this, no? Yeah. You know, modulus of omega, people, 1. Modulus of omega, 1. Therefore, I can write this is equal to 1 times mod z minus 1 plus 2 mod. Right. But you can write, people, this way. But z minus 1 plus 2 mod. When you consider this as your complex number z1, this as your z2, then we can write modulus of sum of two complex number less than or equal to sum of the modulus of the complex numbers, like this. We proved this, no? We know this. Okay. Then you can write this one is nothing but what, people? This is equal to this, no? What is the left hand side of the equal sign we have? This. Right? This. That is nothing but simple A, no? Less than or equal to z1 is mod z minus 1 and this is 2 mod 2. This one is this because this is equal to left hand side we have this, but this is equal to in the question A. This is therefore A. A less than. Well, can you tell me for the right hand side to be maximum, what is this? Z minus 1 mod is less than or equal to. This is 2. Right? Plus mod of 2 is 2. Then this A less than or equal to 4. That is okay. But people, this A mean what? This is a complex number. Its modulus is A. People, modulus of a complex number should always be positive, or the minimum value it can have is, people, 0. Because you know, modulus of a complex number mean length of the corresponding line segment which represents the complex number. No? Length of a line segment never be negative. Then you can write but A greater than or equal to 0. Therefore, we get this answer. We get this answer. Right? That's how we take this answer. Right. Now, people, take the tutorial. In your tutorial, take question number 67. Take question number 67. This is a past paper question. Number 67 is the next question. Number 67. This is a past paper. Some see here number of inequalities available. Let Z be a complex number. Prove that mod Z squared equals Z bar. That you can do. Mod Z greater than or equal to real Z. That also we have proved. Hence show that mod Z1 minus mod Z2 less than or equal to mod Z1 minus 2. People, this part, hence, so that means don't go to the algebraic geometric method. Hence means using that mod z squared is equal to z bar and mod z greater than or equal to real z. That means you have to go through algebraic method. That whole thing available in the previous what lesson we did Friday to Candy group, and I put that to your group also. Get the recording as soon as possible and watch it. I did like that, people, in order to minimize the number of hours we take. Otherwise, that part also today I have to do, then these things I can't cover properly. So therefore, please watch them. Right? Some of the students, people, they don't take the recording at time. I put the message to one group, they take 5-6 days and last moment they request. Right? Yesterday, of course, in the evening I put that, you didn't have any time, but some of the students, they last moment only join the class and saying that and this I joined, you didn't accept me, and so on. So all blames coming to us. So therefore, don't do like that. When you get the link as soon as possible, we have to people register there. The other thing is, when I put the recording, for the same recording, all the time I can't actually with this computer to approve you. So therefore, soon after getting the message, approve them once, I can approve all. Much convenient to both parties. Okay, soon after starting the class, some of the students, they join. Then that occasion, while I am teaching here, I can't accept you. Right. So then you might say, then give this before, 2-3 days before, even though the same situation coming, people. Some of the students say, I didn't get the link yet, please send me it. Already available in the group. Okay. Now here, take that recording and watch that and get the notes. Then the first part you can prove. Deduce that part also available. That also we have done. So therefore, I'm not going to do that again. Now, people, you are given next one like this: z minus I mod. Less than half. Then ask him to show mod z less than 3/2 greater than half. Right. Try to prove that, people. Try to prove that. Something like this, no? The theory part we have proved. Here, the same question, theory part we have proved. Mod z1 minus z2 greater than or equal to mod z1 minus mod z2. This we have proved. Then I am going to take this one, people. Mod z minus I. This. I'm going to apply this. Z1 is this Z. Z2 is this I. By using that theory, I can write this one greater than mod z minus mod I. This way I can write this. Okay. Mod I is 1, people. We know that. Right. People, now here, mod z minus I less than half. This value less than half. Then if we put for this z minus I modulus half, people, still the right hand side is greater, no? Now think like this: x greater than 5. Right. Now if I put to the right hand side a value which is greater than 5, like 10, x less than or equal to 5, then definitely, people, x should be less than 10, no? like that. This thing less than or equal to this. Okay. But z minus I modulus less than half. Then people, I can put without equal sign here half. Here also x less than or equal to 5. But when you put here 10 people, no longer you can see one equal sign. Why? X can take 5. Maximum value x can take is 5. Others are less than 5. When you put to this place of 5 greater value than 5 people, like 10, if you put equal sign here, x equals 10, wrong idea. That occasion, less than sign only valid. Okay. Like that here also, z minus I modulus less than half. It doesn't take half. Then this value is anyhow less than half. If I put half here, people, this equal sign is not valid. Less than sign only valid. Then we get like this. This gives us mod z minus 1, mod z minus 1. Take this right hand side. This way we get first result. Okay. Second result, people. You know, this z minus I modulus and I minus z modulus being equal, no? You know, when we have by this way P1, P2 line on the Argand diagram representing the complex numbers Z1 and Z2, P1, P2 length mean Z2 minus Z1 modulus. P2, P1 length mean Z1 minus Z2 modulus. Since these two are equal, people, these two should be equal. That means by interchanging inside the modulus, the values won't change, right? So therefore, I can write again this thing, what? This thing like this. Z minus I, since Z minus I modulus is equal to I minus Z modulus. I can write I minus Z modulus greater than or equal to I modulus minus Z modulus. This way I can write using this result. I minus Z modulus greater than or equal to this, I can write like that. Then this is 1 minus mod Z. For this one, I can write I minus Z modulus is equal to Z minus I modulus, like this. But Z minus I modulus, people, less than half. Then this can take the maximum value half, but half also it doesn't take, right? Suppose maximum value is 0.49. The maximum value this can take is 0.49. Then the left hand side is equal to that 0.49 or left hand side less than that. But if I put here to the right hand side a value which is greater than 0.49, then no longer this equal sign valid, but less than sign become valid. Understand? So therefore, Z minus I modulus less than half means if I put half here, this equal sign you can't put. 1 minus mod Z. It brings this side, this side. 1 minus half less than mod Z. Then this gives us this way. So therefore, people, inside this what you have? This and this both available. Okay. So therefore, we can write z minus I less than half. Mod z less than 3/2 greater than half. No? Right. People, this same thing you can understand in another way. Another way. Alita means alternative method of understanding this. Can you tell me what is this z minus I mod less than half? What's the easiest way of understanding this? Suppose here we have z minus I mod equals half. What is this? It's a circle with center at I, radius half. Correct, no? Center at I. I is here. Radius half. I means this length is 1, no? Then radius half means this. Right. This z lies on this. But we need what? Z minus I modulus less than half. This. Then people, where should be the region inside the circle, no? From here, when we draw a line like this, suppose here is it z minus I means this length, z minus I modulus means this length. Correct, no? Somewhere here consider a complex number z. Then from here to here we draw a line. Then this length going to be what, people? Z minus I modulus. That length should be half. For that length to be less than half, definitely that z figures should be inside the circle. Should be inside circle. Then only the distance from this I to that point or less than half. Then this region mean, people, inside the circle. Inside the circle means this circle we have draw dotted lines like this. In this region, inside circle, only this z available. Right. Now, z complex numbers available, people, in this region. Right. Now, this imaginary axis, no? This is real axis. This is origin, no? People, now it's obvious now the all complex numbers z should lie in the circle. But what is asking? Asking about modulus of z. Asking about modulus of z. Asking about modulus of z. People, modulus of z mean what? When we consider a point on the Argand plane represented in the complex number z, then modulus of z mean the distance to that point from the origin. From the origin. People, when a complex number lies inside the circle, what is the maximum distance and minimum distance to that complex number from the origin? That is to say, people, from an exterior point of a circle, the maximum length and minimum length to the circle. From this point O, the maximum length is, people, to the circle this. The minimum length is, people, to this. So therefore, mod z minimum, when z lies here, the minimum length from origin to this point we get as half. The maximum length, this. What is that? From here to here 1, here to here half, 3/2. Then mod z minimum is half, maximum is 3/2. Since this point is not on the circle, our z can't be taken at the point this, because on the circle region we can't include to this because we don't have equal sign. So therefore, mod z should be greater than half, and what, less than 3/2. Okay, this region is this. Okay, right. And then we can write people. Therefore, mod z less than 3/2, greater than half. Right. Okay, what's the next part? Here's the next part, people. Right. Right now, by this we just now proved mod z this. Okay. Now read the next part. Now next part we are given. The next part is this. Shade the region R consisting the set of points in the Argand diagram which represent the complex numbers Z for which right Z minus I modulus less than or equal to half, and arg Z is 5/2. Right. People try to shade this region. Z minus I less than or equal to half. Z minus I modulus equal half. Equal half mean people on the circle. On the circle. Less than half mean inside the circle. Right? So therefore, this region I can now draw. I take the same diagram. Now, no longer we have dotted lines. Right. Then the required region is people. Z minus I modulus equal half mean on the circle. Less than half mean inside the circle. Then what region we need? Yeah. On the circle and inside the circle only, this is a complex numbers available. Right. Now, next thing we need is people this. Arg Z equals 2 pi by 3. First we'll take arg Z pi by 2 first we take. Complex numbers whose argument is pi by 2 lie on this imaginary axis. Right. And complex numbers whose argument 2 pi by 3. People, 2 pi by 3 is this. When we construct a tangent from this origin to this circle, here, look at this. This way. What is this radius? Radius is half. Radius is half. This length is 1 unit. If I take this angle as theta, sin theta is half. Then theta is 30. Then this whole angle, this is 90. This is 30. Then 120 coming. Then arg 2 pi by 3 line is this. Then we need people that argument should be between, it should be greater than or equal to pi by 2, less than or equal to 120. Yeah, then that arguments lie between imaginary axis and this line. In between these two lines only, this region available. Okay. And the meantime, we should consider on the circle and inside the circle. Then people, what is the portion we have to consider? The portion we have to consider is this. This portion, no? That portion only we need to consider. That is the common region. Okay. Right. Then you can take it as theta, construct a tangent like that. Okay. Then we can write the required region is therefore required region is this region. The required region is people. This part we have to exclude, right? Right. Then this is the portion. Then people, when you consider any complex number in this, somewhere here consider complex number, then Z minus I mod less than or equal to half condition satisfied. Okay, Z minus I means what people? This is I, no? the distance from I to complex number. I is here, from here to the complex number, the distance is this. That should be less than or equal to half, correct? No? When the complex number is inside this circle or on the circle, this equal sign become valid, right? And any complex number on the circle or inside the circle, when we consider its argument, people greater than 90, less than 120. Both conditions are satisfied. Therefore, this is the region R. Region R is this. Right now, who got this?